So if you've only ever messed around with ideal circuits, you're missing a huge piece of the puzzle. I mean, in the real world, pretty much every load, from a simple motor to a complex power supply, has inductance. And this electrical inertia, as we call it, completely flips the script on how a circuit behaves. So today, we're going to roll up our sleeves and tame that inductive load in a single-phase rectifier and see exactly how it all works.
All right, so here's our roadmap for today. First, we're going to see why just adding an inductor creates two totally different realities for our current. Then, and this is cool, I'll show you this powerful map that lets you predict which reality your circuit is living in. After that, we'll put it all to the test with a real-world case study, and then we'll wrap up with the most important takeaways you need to know.
Okay, let's dive right in. You know, to really get a handle on the complicated stuff, we've got to start with what we already know. We'll begin with a circuit you've probably seen a dozen times, and then we'll add the one little component that changes absolutely everything.
So over on the left, that's your classic textbook example, right? A simple resistive load where the current just perfectly follows the voltage. But on the right, yeah, that's the real world. That's the guts of a motor drive. That whole mess of components you see is all about one thing: managing energy. And that's the key difference. Real circuits have to store energy, and that simple fact complicates things in a very, very interesting way.
And this is our new, much more realistic model. We're adding an inductor, that's L, to store energy, and a DC voltage source, E, which could be anything, maybe the back EMF from a motor or even a battery you're trying to charge. This simple RLE circuit is a way better model for what's actually going on. And believe me, that inductor is about to change the entire game. You know that one little component we just added, the inductor? Well, it creates this fascinating split. It's like the circuit suddenly develops two completely different personalities. It can operate in one of two totally distinct modes, either continuous current flow or discontinuous current flow.
And it all comes down to energy. In what we call continuous conduction mode, or CCM, the inductor is beefy enough, it stores enough energy to just keep pushing that current through the load. Even when the input voltage dips low, the current never, ever stops. But in discontinuous conduction mode, or DCM, the inductor is a bit smaller, and its stored energy just runs out of juice partway through the cycle, causing the current to drop all the way to zero for a little while. And here's what those two modes actually look like. See? In continuous mode, the current is always on, it just has this little ripple to it. But look at discontinuous mode. The current literally stops, and then has to start all over again, every single cycle. And listen, this isn't just a pretty picture difference. This has huge implications for everything from component stress to the quality of power you're delivering.
So here's the secret sauce for what's happening mathematically in continuous mode. The current is basically a mix of two things: the part that's forced by the AC source and the natural part that comes from the inductor releasing its stored energy. And that natural response? It's the glue that holds the whole thing together. It's what makes sure the current from one cycle connects smoothly to the next one without ever hitting zero. And this is a perfect example of why discontinuous mode can be a bit of a headache mathematically. See, we know when the current starts. That's easy. It's at an angle called alpha. But figuring out exactly when it stops, that extinction angle beta, well, that means solving something called a transcendental equation. Yeah, there's no simple, clean formula. We've got to break out the big guns. Numerical methods, lookup tables, that kind of thing. Okay, so we know these two modes exist. That's great. But the real question for any engineer is, if I give you a circuit with certain parts, how can you predict which mode it's going to be in before you start doing all the heavy math? Well, this is the answer. This boundary map. And it is an absolutely killer tool for engineers. Just by calculating two simple, normalized parameters from our circuit, we can pinpoint its operating mode. The vertical y-axis is just the ratio of your back EMF to your peak supply voltage, and the horizontal x-axis is the load impedance angle, which basically tells you how inductive your load really is. And the best part? Using this map is super straightforward. Here's what you do. You calculate your voltage ratio, that's your y value. Then you calculate your impedance angle, that's your x value. You find where they meet on the graph, and it will tell you instantly if you're in the continuous blue zone or the discontinuous red zone. Simple as that. Theory is great, but let's put all this theory into practice. What do you say? We're going to apply everything we've just talked about to a practical example. We'll walk through the analysis and then check our work, just like you would on a real-world engineering problem. Okay, so here are the specs for our circuit taken from a classic textbook problem. We've got a 120-volt RMS 60 Hz source.
It's feeding a load that has 2.5 ohms of resistance, 6.5 millihenries of inductance, and a 10-volt back EMF.
All right, first things first. Before we can calculate anything else, average current, RMS current, power, you name it, we have to answer the single most critical question. Which mode is this circuit operating in? Continuous or discontinuous? Because the math is completely different for each one.
So, the standard playbook here, when you're not sure which mode you're in, is to make an educated guess. Since most real systems are actually designed to be in CCM, we'll start by assuming it's continuous. Then we use the continuous mode equations to calculate the current right at the beginning of the cycle. And if that number comes out positive, boom, that means our assumption was right all along.
And after running the numbers, we find that the initial current is 32.8 amps. Since that is definitely greater than 0, our assumption was correct. The circuit is in fact operating in continuous conduction mode. So now we can proceed with confidence using the right set of tools for the job. So now that we know for sure that we're in CCM, we can figure out all the circuit's vital signs. We've got our average and RMS currents for the diodes in the output. We're delivering just over 4 kilowatts of power to the load, and we have an input power factor of 0.84. These numbers give us the complete performance picture of our circuit. Now that power factor is really important, 0.84 lagging. It's not a perfect one. So what's the deal with that? Well, think about it. A rectifier, by its very nature, is a nonlinear load. It chops up the nice, clean AC sine wave from the source and draws a current that's, well, pretty ugly and distorted. That distortion, plus a phase shift, is what brings our power factor down. This is a huge deal in real-world power systems.
Okay, but how do we really know our math checks out? We verify it. A fantastic final step is to build this circuit in a simulation tool like PSpice. This lets us compare our theoretical pen and paper model against a much more detailed simulation. Our math gave us an average output current of 39.22 amps, while the simulation came back with 31.83 amps.
They're in the same ballpark for sure. But why the difference? This is a crucial lesson. Our analytical model assumed perfect, ideal diodes with 0 voltage drop. PSpice, on the other hand, uses a realistic model where each diode has about a 0.7 volt drop when it's on. That little bit of real-world imperfection changes the effective voltage driving the load, and that alters the final current. It's a great reminder to always be aware of the assumptions you're making in your model. Woo! Okay, we have covered a ton of ground today. So let's just boil this all down to the key things you really need to walk away with. All right, so what's the bottom line? Number 1, inductors smooth out the current. 2, this energy storage creates our 2 modes, continuous and discontinuous. 3, and this is crucial, we can predict the boundary between those modes. 4, your analysis method has to match the mode you're actually in. And finally, number 5, we saw that our theory, even with its simplifications, gets us remarkably close to what we see in a real-world simulation. And that is why all of this matters. Look, mastering these single-phase rectifier concepts, it's not just some academic exercise. This is the fundamental foundation you absolutely need to understand and analyze the much bigger, much more complex three-phase systems that are the true workhorses of our modern industrial world. You've got the tools now. So the only question left is, what are you going to power next?